Hi everyone, I hope you're all healthy and well. Welcome to the next talk in our Golden Webinars in Astrophysics series. Our speaker today is Jay Pasachoff, who is the Chair and Field Memorial Professor of Astronomy and the Director of the Hopkins Observatory at Williams College. My name is Evelyn Johnston, and together with Thomas Putzia, Elizabeth Artur de la Villarmoa, Demetra de Chico, and Paula Ronco, we have organized today's webinar for you. Unfortunately, this will be my last Golden Webinar as co-host, and I'm currently joining you from my car at the side of the road, just outside of Villarica, which is the only place I could find signal. As of January, Maria Paula, Elizabeth, and Demetra will be taking over from me. As in our previous webinars, we have arranged for simultaneous language interpretation provided by Mr. Patricio Gonzalez, who will be simultaneously translating for us into Spanish. En sus dispositivos pueden escuchar la interpretación al español de la conferencia al pinchar el botón de interpretación que se encuentra en la parte inferior derecha de la ventana de la aplicación Zoom y seleccionar español. Before we continue, we'd like to acknowledge the generous support from the Center for Astrophysics and Related Technologies, also known as CATA for its Spanish acronym.
Thank you so much for all your feedback and comments. If you're watching a recording of this talk on YouTube, please leave your comments below. If you would like to support the Golden Webinar series or give us feedback, please send us an email. If you have any questions during the talk, please type them in the Q&A window. You can upvote questions and comment on them also. We will select the best questions for discussion after the talk. Before we begin, we would like to briefly introduce the other panel members that are with us today. There's Jay Pasachoff, our speaker, Patricio, our interpreter, Evelyn, Paula, Elizabeth, and myself as co-hosts. We have also the great pleasure welcoming Felipe Barrientos, the director of the Institute of Astrophysics at Pontificia Universidad Católica, our graduate student, Álvaro Valenzuela, and our guest from Chile, Hans Zinnecker, who is an astronomer emeritus and ex-deputy director of the Sophia Science Center at NASA Ames. And finally, we have our excellent Q&A managers, Ricardo Acevedo and Daniela Fernandez with us today.
It is our great pleasure to introduce Jay Pasachoff as our speaker today. Jay completed his PhD at Harvard in 1969 and carried out several postdoctoral fellowships at the Harvard College Observatory and at the Caltech before joining Williams College in 1972. After that, he has taken sabbaticals and has visited too many other institutes, including the University of Hawaii, the Institut d'Astrophysique de Paris, the Institute for Advanced Study in Princeton, the Harvard-Smithsonian Center for Astrophysics in Cambridge, Massachusetts, Caltech in Pasadena, California, and the Carnegie Observatory is also in Pasadena. He is currently a Field Memorial Professor of Astronomy at Williams College and Director of the Hopkins Observatory.
His research interests span a wide range of solar system physics, from using solar eclipses to study how the corona of the sun becomes so hot, to using transits of Mercury and Venus across the sun as an analog to exoplanet studies. Throughout his career, he has written many books on the sun and other planets, as well as several biographies of famous astronomers, which he wrote with his wife, Naomi. As a veteran of 70 solar eclipses, including 34 total solar eclipses, and the chair of the working group of solar eclipses at the International Astronomical Union, there is no one better to prepare us for the spectacle we will see on Monday here in Chile. And so we will now hand over to Jay to let us about the science of solar eclipses.
Thank you very much for this nice introduction. It is my pleasure to be again talking to a Golden Webinar, or to a talk anyway at the Pontifical Institute, Pontifical University, because I lectured for Thomas Putzia less than 2 years ago, just before the July 2nd, 2019 eclipse. I have a group of people at the eclipse site near Pucón, who've been coming over the last few days with a lot of equipment. Rainbows are very pretty, but we don't necessarily like to see them when we're about to have an eclipse, and this is the view from Pecan this morning. So I will talk for under an hour now to talk about some of the past eclipses and observing eclipses, and I do thank you for the invitation. My work at Eclipses now has been specially covered by the Solar Terrestrial Program of the Atmospheric and Geospace Sciences Division of our National Science Foundation. I've had student support from the NASA Massachusetts Space Grant. We've been limited by bringing students this time by COVID restrictions from my university and from MIT. I do have one alumnus from last year coming courtesy of the Sigma Xi, the Honorary Scientific Society. I will talk a little bit about the last two eclipses and then talk about what we're going to do on Monday. This is a composite image from the 2017 eclipse, which went across the United States, the whole continent of the United States from upper left to lower right. Now the sun is 1,000 times brighter here than here. Well, let me say, first of all, this is a picture of the moon. So this is the dark side of the moon, the side that's facing us. The other side is illuminated. So it's hiding the bright sun. Everything, therefore, is about 1 million times fainter. And even with that total amount of light that is 1 million times fainter, we do have the solar corona that we're seeing here that is 1,000 times brighter here than here. So no single image with electronics or with film can capture it all. So this actually comes from dozens of images that have been carefully put together. So there's a lot of computer work we do too. The shapes we see here in the solar corona are held in place by the solar magnetic field, which was discovered over 100 years ago by George Ellery Hale at Mount Wilson. And it's as though there's a bar magnet through the sun. We see these polar plumes like iron filings from a bar magnet, but there are many localized regions of high magnetic field, thousands of times stronger than the average magnetic field of the sun or the earth. And they show as sunspots on the surface. And then we have these streamers that come out. And depending on the phase of the sunspot cycle, the streamers are more concentrated toward the equator, as you see here, or at a maximum of the sunspot cycle, even higher latitude to the point where they'll even hide these polar plumes. There are other new ways of studying the sun that are very exciting. And one is just in engineering tests now, the Daniel K. Inouye Solar Telescope, named after the long-term senator from Hawaii, where this has been built on Maui. And you can see now that taking a little part of the sun, they concentrate on an even smaller part here. And we see in this the boiling phenomenon known as granules. So this field of view is only, well, the granules are only 1,000 kilometers or so across. The telescope itself is about 10 stories high, partly because there's a lot of instrumentation, partly because it's the biggest telescope for the sun ever built, with a mirror 4 meters across. And also the telescope is located high up because there can be ground turbulence that we want to be over. It is unusual for a picture of the sun or part of the sun to be on the front page of newspapers, and even above the fold, as the saying goes, for a large part of the front page. Last January 30th, 2020, was one of the first images taken in an engineering test of this telescope, the sun's churning face. And here we have a little animation here, and you can see how these granules, as they're called, move around, and they boil up in the middle, and then the gas moves to the edges of each granule and then sinks. And then sometimes it concentrates the magnetic field. And a little closer view here, you can see some of these granules. So there are many things that will be discovered with this new telescope when it goes into full mode, including some observations of little bits of the corona. But the mirror is so big that they can only look at a small field of view, or else the heat from the sun would cause damage. And so we will discover things on the corona with it when it is going. And I look forward to studying the outer layers of the sun with it. It's not the first time the sun took up a lot of room in the New York Times. This one was from just over 100 years ago. On Monday, it will be 101 years. And there was a picture of a technique that George Ellery Hale developed to take pictures of the sun in single colors. So this is a color in the red called H-alpha, primary gas at around 10,000 degrees in what is called the solar chromosphere, especially because of the colors that it emits. And for scale, you see the Earth there. So there are 100 Earths could fit across the sun, which means because it's a volume, 1,000 Earths would fit in the sun. Here's another view of that page here, a little higher contrast that was made on December 14th, 1919. Rob Rutkowski has been up on top of Haleakala at a high volcano and the island of Maui, photograph especially the Milky Way, the top of some of the telescopes, including this new solar telescope up here at the edge of the field. This is an elevation of 10,000 feet or over 3,000 meters. The idea of calculating where an eclipse would be visible on Earth really started with this map by Edmund Halley in 1715, where he projected the shadow of the moon, the darkest shadow, the umbra, across the face of the Earth. And here's the center line, and this is part in the umbra. There'd be partial phases to the north and the south. And in the text and below, in the broadside, he said the curious had desired to observe it, especially, and that will help predict the like appearances for the future. So he started what we now call citizen science, where we not only have the professional astronomers observe the phenomena, but other people too participate. In the eclipse in 1918 that went across the United States, the prior one that went from west to east all across the continental United States, film was too slow to capture the shape of the corona very well, or to see it far enough out. So a painter named Howard Russell Butler was invited by the U.S. Naval Observatory to travel with them to Goldendale, Oregon, to take notes during the 2 or so minutes of the eclipse, and then to translate it to an oil painting. You can see the reddish chromosphere and these what are called prominences also in H-alpha at the edge there. And you see they had some clouds also. They were seeing it through clouds. And he was so excited to do this that he then went back in 5 years later to California when there was an eclipse. You can see the shape of the corona is more extended towards the equator here, so it must be closer to solar minimum. There was a nice hole in the clouds on that occasion, and he went back 2 years later to Connecticut. These are big paintings that are more than 2 meters high, and they were for years, for decades, over the entrance to the Hayden Planetarium in New York, and he also painted some half-size versions. This is at the planetarium at the Franklin Institute in the theater near there in Philadelphia in the United States. He went on to paint the 1932 eclipse, and then also to take a photograph that had been observed at the Mount Wilson Observatory and draw this chromosphere, the reddish chromosphere, and the prominences at the edge of the sun. And then during this 1918 eclipse, he not only painted the corona, but also looking ahead, and you'll see photographs like this later, you can see the shadow, the umbra approaching. And then if you look far enough away, you're seeing hundreds of kilometers away where there isn't the umbra and some light scatters in. And for the same reason that sunsets are reddish, we see this reddish effect all around us during totality. His paintings have now been torn down and are in storage, where my wife and I were able to see them at a secret location. And this Art Deco image was replaced by an ultra-modern planetarium in New York City 20 years ago. Here is the sunspot cycle, in which it's graph of something called sunspot number, which is not actually the number of sunspots. It's actually 10 times the number of groups plus the number of spots. So it's weighted towards how the sunspots are grouped. And this is the most recent cycle going back a dozen years. The average length of a cycle is 11 years, as most of you know, but it can vary to be a year or two shorter or longer than that. So we had a minimum here back in 2008, 2009, and a maximum. The two different hemispheres of the sun, northern hemisphere, peaked at different times in 2012 and 2014. And now you see through 2018, and these yellow is the daily views, most of the days of the year there were no sunspots at all. And we're just now starting up in the new cycle of sunspots. So my group is very interested in studying the corona over the sunspot cycle. It's a whole cycle of activity of various kinds. The records go back hundreds of years. Maybe there's some longer cycle. Well, here, in addition to the 11-year cycle, here's the double peak of this most recent cycle, and here we are now. And just recently, the European Space Agency has put together a map of the ultraviolet image of the sun, which shows hot gas at coronal temperatures from when this solar and heliospheric observatory was launched back in 1995. So we see they had a solar minimum there, and it went to solar maximum. You can see that the sunspots tend to be in bands north and south of the equator. It shows very clearly here in 2000, for example. Then we went back to a solar minimum here around 2009, 2010. And then here's the solar maximum here. We see the bands of the sunspot active regions, as they're called, and also these regions of slightly less temperature and lower density known as coronal holes. And then we went into the solar minimum, 2017, 2018, and now we're just coming out with the first sunspots at high latitude. Graphs have been made for over 100 years showing the latitude. So this is the latitude on the sun in addition to the brightness and the number of the sunspots. The number of sunspots is shown as brightness. And you can see that as each cycle progresses, the sunspots come closer and closer to the equator. They don't usually actually reach the equator. This is known for obvious reasons as the butterfly diagram. And we're just starting to see a few spots now in the top, which shows the beginning of the new cycle. This is a measurement at the bottom of the area of the sun covered with sunspots, and that correlates with the sunspot number, though it's not exactly the same. Here's an image from one of our earlier eclipse expeditions when it was solar maximum, and you can see that there are so many streamers here that they go out in all directions and they cover up the polar plumes, and you can see some of the outer streamers there. Yes, so that was back here at solar maximum here. It's wonderful to be outside in the total eclipse. So I hope the various of the people who are watching have had the chance to do that and will have the chance again. Here we are at an eclipse in India. This is me looking up at the eclipse in the sky. There's sort of a dark moon here that's, and the brightness of the corona there. You can see the effect of looking near the horizon, and two of my students here helping to observe the eclipse on that occasion. Now, recently, we're just coming out of solar minimum. Here's an image posted by Brian Goff showing how blank the sun was in this hydrogen alpha. But you could see that even so, there was some magnetic field, and we had these prominences on the edge of the sun. So this is back in July. Now, starting last week, say December 1st, there were some sunspots on the sun. So in ordinary light, we see the sunspot has what's called a dark umbra and a lighter penumbra. So the word umbra gets used in two different ways. Of course, it means shadow from the Latin, but on a sunspot, it's the dark central region, and in an eclipse, it's the dark central region as it falls on the Earth or as it goes through space. Anyway, this background image is the magnetic field. You can see that there are opposite polarities here, and they don't show in the white light, the ordinary light image, but we do get the penumbra and around the central umbra in the sunspot. So this was last week's on December 1st, and then the sun rotates. So here's December 2nd, and then there was two other groups here of sunspots. This one is a bigger sunspot than that. Notice they're only in the southern hemisphere, not in the northern hemisphere. And you can go every day on your website on your computer to spaceweather.com and see the sunspots from the day. Here's the next day, and they've rotated a little bit. So the sun is in differential rotation. The equator rotates faster than the poles, and the magnetic field under the surface gets wound up and eventually kinks and pushes up to make the sunspots. And jumping a few days to December 8th, so 4 days ago, we had a sunspot that's rotated from the left side here into more central in the disk and just a faint one. By the next day, that faint one has disappeared, and this is closer to disappearing over the limb. So remember that there's another half on the other side that we're not seeing. So here's yesterday, and this one is about to disappear on the limb. And the question is, during the eclipse on the 14th, will we have some features on the edge to make some interesting structure for us to study? So today, the image from today just shows a sunspot coming around the edge over here. So that will be more on the disk. So we do hope to see some activity on the edge. And this one is disappearing, and whether in a day and a half from now or 2 days from when the picture was taken, it may be too far around the other side to make something on that edge. So here is Halley's view, again, of the umbra. And this time the umbra is going across the Pacific Ocean onto Chile and Argentina and out in the Atlantic Ocean. So Halley did this map in 1715, but the people sent in the observations he asked for, and he used that then to make a new map with the adjusted position of the 1715 eclipse. And you can see this path here is a little different place on the edge here. So it was a few kilometers away and a few seconds in time, and he improved his predictions for the 1724 eclipse that went down to the right and went over to the European continent and was observed then in France there in addition. I showed this picture at the beginning, and let's look at it again for a bit. I'm working with Professor Wojciech Rushin from Slovakia and a computer specialist, Roman Vanur. There are a few people who specialize in putting together dozens of images. In order to make this selected set of things, you can see that it's a porcupine kind of structure going out in all directions, and we're just seeing the projection against the plane of the sky. So here are the polar plumes, and here are some streamers near the equator on that occasion in 2017. So this was 68 individual images, and one of the things that I like to study is some loops of coronal gas near the edge of the sun, and this gas here is 1 million degrees or so, And the question is how it gets heated to 1 million degrees. Now, temperature doesn't mean that you're going to burn yourself because the density is very, very low. So there are not that many particles around, electrons, protons, but the ones that are moving very fast. And that's what we mean by high temperature. And there are various predictions in just what mechanism heats the corona to millions of degrees. One of the predictions uses some of the newer technology to look for oscillations, vibrations of loops near the edge of the sun with periods of less than 1 second. It used to be to take a picture of the sun, when you're using film, you needed 30 seconds to take a picture with film, and obviously you're not going to find 1 second oscillations with a 30-second exposure. But now that we have these very good electronics and fast electronics, we have techniques of looking several times a second and looking for these oscillations. And we have some indication from past eclipses that they exist. My student, Alan Wang, took a heliophysics course from me last year, and working with the math professor, he worked with me on a senior thesis last year, and another senior from Williams College last year, Christian Lockwood, is at the moment been traveling to Chile from a NASA expedition to Australia to watch that Japanese spacecraft that brought space dust back from an asteroid last week. He was part of a NASA team to photograph the re-entry. So that was very exciting, and I'm looking forward to hearing details from him. And NASA flew him in their Gulfstream business jet to Guam, and then Wake Island, and Hawaii, and San Francisco, and then so he's been flying down via Houston to Chile to join in the Eclipse expedition. So I've been working with my students on studying the science behind these images. In 2017, we had the first all-American eclipse, really ever, because the one 99 years earlier hit the Bahamas, which are part of the British Commonwealth. But here we see just from Oregon across the continental United States, we had the eclipse, and I wanted to hit it as soon as possible. You can see off to the sides we get the partial eclipses. So here's the shape, and we went to Salem, Oregon, and then I've learned a lot of geography, even of my own country, the United States, from following the path of the eclipses. Notice that the eclipse, this shape, is not actually just an ellipse, and that's because the moon is not quite round. We can now map the moon in 3 dimensions. The NASA's Lunar Reconnaissance Orbiter maps the moon in 3 dimensions. And there was a Japanese Kaguya spacecraft that did that slightly earlier. And so now that we know the actual shape of the moon, we know how the light goes around the edge of the moon. And it turns out we have this polygonal shape instead of just an ellipse. Ernie Wright of NASA's Goddard Space Flight Center is in the visualization studio, and he's worked out how the umbra and the penumbra of the shadow hit the Earth and went across the United States on that occasion in 2017. I had a lot of students with me for this American eclipse. I had some scientific colleagues with me then, and then we had 8 undergraduates from Williams College, juniors and seniors, 3rd and 4th year students, and several of our alumni who were graduate students, and an additional group of alumni. And so we worked on a balcony of the math departments of a university in Salem, Oregon, the Willamette University. And we had a lot of cameras and filters here, and telescopes and telephoto lenses. Here is the group from Williams College on that occasion. And I actually started taking students with me from even before I came to Williams College. I had been appointed, and I came a few months before my job at Williams started on July 1st, 1972, to recruit 4 students to go with me to the 1972 total eclipse in Canada. So I've been working with students ever since to observe total eclipses. Christian has put together this composite. Now, the everyday sun is, as I said, about 1 million times brighter than the solar corona. So we need special filters for this observation. And so these are taken through those filters. And anybody not in the zone of totality needs to use the filters, or sometimes we put the filters in glasses. And there are millions of these glasses left over from the American eclipse in 2017. So we brought a few thousand of them with us to Chile. An organization called Astronomers Without Borders has collected them. That's a pun on the name of medicine, Doctors Without Borders. So Astronomers Without Borders works around the world to do good things in astronomy, and they've collected a lot of these very lightly used eclipse glasses, and we'll be distributing some in Pucón. And my colleague, also Patricio Rocco from the University of Chile, has distributed a few thousand in his travels in the zone of totality too. Anyway, at the beginning of totality, we take the filters away, and these are without a filter. And then the last beads of sunlight shining through the valleys on the edge of the moon are known as Bailey's beads. And then the last one is so bright it looks like a diamond on a ring, is known as the diamond ring effect. You see a little reddish chromosphere here. And then when that's covered, we can see, well, more prominences. And then just depending on whatever exposure you use, you see more corona or less corona. Now that we know the actual shape of the moon, Xavier Dubier from France, who is with us in Pucón now, has calculated the matching of these Bailey's beads, and we take our observations to try to match them. And you can see here that the size of the sun, if it varies a little bit, well, it doesn't actually vary, but if the size, our knowledge of the size varies, would depend very accurately on the actual shape that we'll see there. And here's a nice prominence, as we saw there. And here's a beautiful prominence on the edge of the sun. In 2019, I was given 4 slots on Cerro Tololo, part of the Cerro Tololo Inter-American Observatory. And I was already committed to go to the center line in La Higuera. So I had 4 students and alumni go with equipment to there, as you'll see in a minute. Christian Lockwood was with me at our site, and here are some composite images again. So these were ones that he made as part of his undergraduate thesis, the polar plumes and the equatorial streamers. From my article in the journal Scientific American, we can see here this drawing that the sun was 15 million kelvins in the center and gets cooler by as you go out, and radiation carries energy out. And then the outer third of the sun or so boils and makes that granulation that you saw the movie of on the surface. And so if we move to the surface, then the sunspots are in that granulation. And then above the surface, we have the coronal loops for which we're looking for oscillations. Here's another composite showing that over an hour and a half or so, we get the gradual covering of the moon, of the sun by the moon. And then eventually we take the filters away when we get it completely covered and see the totality. Now, there are some other ways of studying the corona, and one is to make an artificial eclipse, but because of that extreme variation in brightness, we can't make an artificial eclipse yet as good as a real eclipse. So on this telescope of the European Space Agency, the Solar and Heliospheric Observatory, the US Naval Research Laboratory has what's called the coronagraph, but it blocks not only the everyday sun, but also a region almost twice the solar radius around it. And then just so as you're not looking at a black surface, we've pasted an image from a NASA spacecraft there in the extreme ultraviolet. And then once we've blocked that area from this Naval Observatory camera, we can see streamers going way out, and we can see that every half hour or so all the time. And so sometimes you discover comets that are going close, and there are eruptions that go out that can be seen. But there is a gap in the inner corona, and so only on the days of eclipses do we get a complete view of the sun from the surface, where there can be active regions, through this corona that we see at eclipses, and then into the corona that we can observe from space. Here is a weather satellite over the United States here. Here's the United States, Baja California, and Mexico here. And we're down here, of course, in Chile, and I guess people who are all around the world are watching on Zoom. But you can see this is a real phenomenon. There really is a shadow. There's the umbra going across the Earth's surface and then meeting up at sunset there. This is a series from the National Oceanic and Atmospheric Administration, NOAA, and then some bright person figured out a dozen years ago or so that the spacecraft's cameras may be pointing down at the Earth, but the solar panels are pointing up at the sun. So now there's a solar telescope in the solar panels with 6 different filters covering different temperatures on the sun. And our alumnus, Dan Seaton, works with those. Here's just a close-up of the path across the United States. And you can see that we had a whole clear area here, some clouds in the middle, and people got views through clouds near the end. So the question is, given how many clouds there are on the Earth's surface, do we get clear weather to see an eclipse? And we got a lot of clear weather in 2017. Even though the eclipse itself is only total for 2 minutes or so, it takes a couple of hours to go across the width of the United States. So you can see some features here that change even within 1 hour distance from partway across the United States. So we can measure these velocities of change. And the sky was so clear, we could even see features on the side of the moon that are facing us. So last July, 2019, here's the shadow about to hit Chile here. And here's the path of the eclipse, which peaked over the middle of the Pacific Ocean. So there it was slowest, and because the Earth rotates faster at the equator than lower down, just because it's got further to go around, it keeps up a bit. And my colleague Glenn Schneider was able to photograph for 8.5 minutes instead of just a couple of minutes, 2.5 minutes we had in Chile there. And here's the shadow going across and meeting us here. So then the eclipse was low in the sky and only 13 degrees above the horizon. And then it was the winter time, so we worried about the marine layer and weather and clouds. And it turned out that there was a whole region that was very clear, and we were able to see it in excellent conditions. Here is Ernie Wright's animation of the umbra coming across from the sunrise point. And here's where there are partial phases seen here. You can see what the eclipse looks like from those different locations. And then the umbra is foreshortened here, and then more or less straight down at the peak. And then you see we still have only a fraction of the sun occulted there, but now it's going to be increasingly occulted as the umbra comes towards Chile. And you see it was further north in Chile than we are having eclipse this year. It gets foreshortened here and ends at sunset just before the coast of Argentina on the Atlantic. My colleague Aris Voulgaris from Greece brought wonderful cameras and spectrographs. And so at the beginning of totality, there were obviously here two valleys aligned on the edge of the moon. So we got more or less a double diamond ring effect. One, of course, is a little more persistent than the other. You can see the chromosphere. And then in between, for a couple of minutes, the corona. And then the next contact, when the moon reached the other side of the sun and the little bead developed, we get the diamond ring effect here, and then another bead. So we're very pleased with these observations. And we have a series of scientific goals. We were studying the magnetic field changing over the sunspot cycle. Sometimes there are coronal mass ejections that come out to space. We were studying hot gas with spectrographs and certain colors that show argon that has lost 9 of its electrons, or iron that has lost 13 of its electrons. I mentioned looking for solar oscillations in the corona as a source of heating. I mentioned changing the velocities, and I'm working also with Professor Marcos Peñalosa Murillo from Venezuela to find the effect of the cutting out the sun so abruptly when we get to totality on the atmosphere. One of our collaborators, Michael Thomas Roman, American, now at Leicester University in the UK, just arrived at our site in Pucón in southern Chile to help study these effects. So here's the sunspot graph that I showed you again. And so we had no sunspots for most of a couple of years, and now we're starting to have sunspots. And just where it will peak and how high that peak will be is the subject of much debate, and there are calculations that indicate that this may be another low cycle, but not everybody agrees with that, and we just will have to watch. So for this last eclipse in 2009, we had people at the Cerro Tololo Inter-American Observatory at the 2,200 meters. And I was at the center line and had 2.5 minutes of totality, so we had an extra 30 seconds of totality. And either one is plenty of time to take a lot of images. Now we have such sensitive cameras. And then it was clear even at sea level, though we had worried in advance. And at the airplane, almost 8.5 minutes there. And again, we're supported by various ways for our faculty and students and equipment, but especially now from the U.S. National Science Foundation's Solar Terrestrial Program with the Atmospheric and Geospace Sciences. So here's where I was here, and we have these wonderful maps from Xavier Jubier that you can just click on the path anywhere and get all the details here in the altitude and azimuth. So I have all that information for the eclipse that's coming up on Monday. You can see how elongated the umbra is because it's around the curvature of the Earth. You can see that it ended before the Atlantic coast of Argentina. And here is a video, an animation, and you can see the umbra in the sky. And when the umbra moves up enough, then we'll get the diamond ring effect there, and totality will be over. But you can see how wonderfully clear the sky was from our site on the center line in La Higuera, and we're looking over the town of La Higuera here. Dr. Dan Schechter made this series of images, mostly through a filter, but one during totality without the filter, showing the umbra effect here. David Slisky had this setup of telescopes there, and he has brought these same telescopes and power mount as it's called, and computer control to Pucón now, and we'll see what observing we can get on Monday. So we remain hopeful. Here it is in front of the 4-meter telescope at the Cerro Tololo Observatory. From this higher altitude, the sky was darker, and here is the beautiful view of the eclipsed sun in the middle of the umbra here, and then looking out of the umbra at the edges there. you've seen this image here. This is now doubled up in the second contact and third contact when the moon goes in the sun and comes starts to come out from covering the sun. And here are calculations that Xavier Dubier has made, and we can match over time the details of the Baily's beads, and we hope to do that this time. We have some video and other measurements to make that with good timing, and we'll work again on the best value for the size of the sun. At La Serena, we were not quite on the center line, and so it was not quite as, and from sea level, it was not quite as dark as it was from 2,000 meters, but it was completely clear. And my son-in-law made this wonderful image of the eclipse in the sky. And working with my grandson, Sam, the view of the diamond ring effect here. And these are artifacts in the camera that are very attractive. And we see the corona there. So here, again, is the image that you've seen, especially from Aris. And we've studied them, and we've worked with these three students I had with me in Chile and Aris Bulgaris and I were unable to come this time because of various COVID restrictions, but Alan Slisky is there. Kevin Reardon is back in Boulder, as is Dan Seaton, and then Ronald Kaplan, Cooper Downs. Here, these colleagues, Jonathan, worked to make predictions in advance that I'll show you in a minute, but we're co-authors on some papers presented at meetings and in the proceedings of the meeting that was going on then in Copiapó, Chile. And I did give a lecture similar to the one I'm giving today to the symposium in, well, it was Zoom, but it was supposed to be in Argentina, an IAU symposium that's still going on based in Chile. We were supposed to be in Bariloche. In any case, these colleagues from San Diego, California, have a company called Predictive Science Incorporated, and NASA released the day after the eclipse their bluish prediction, fading in and out with our preliminary composite of measurements, and then so their prediction is really very good, and then any deviations can be used to improve their methods of prediction for the next time. So here is not fading into each other, but here's our streamer here and another streamer here, and then a wider streamer over here and some narrow stuff over here. So we're working on predicting that. And they have released their prediction that I'll show you in a minute. Now we also had spectrographs and could study the different colors in great detail at the edge of the sun. In 1868, this yellow line showed up and wasn't quite where the lines from sodium in the salt that you see blazing yellow if you drop salt into a flame. So they called this helium because it existed only on the sun, and that was the discovery of helium. Now we have this iron that's lost a lot of electrons from 1.5 million degrees or just under 1 million degrees. You see a little faint reddish here. So when we're at solar minimum, the sun's a little cooler, and this spectral line is brighter than this one. And then and that's what we expect to have again on Monday. But then the sunspot cycle will be extending and with more sunspots, and the corona will heat up a bit. And in 2 or 3 years, then this spectral line in the green will be brighter than the one in the red. This is another of the sunspot graphs, but this one shows on it various spacecraft and the durations of their life in space. And you see a number are still there. The current weather ones with the solar-facing cameras are here, and NASA has the Solar Dynamics Observatory and European Space Agency Proba 2. The stereo spacecraft from NASA has 2 different spacecraft that appear around the back of the sun a bit. They're not with the Earth in its orbit. So we do try to see what's coming around. And Hinode is a Japanese spacecraft with some American instruments on it too, and for high resolution observations here. And then I showed you the SOHO set of images over the time since 1996. So using the GOES image, the weather satellite image from Dan Seaton here in gas from the chromosphere, fit into our image from the eclipse with some polar plumes and some equatorial streamers. We can compare these. These are several different temperatures here in the images from the GOES spacecraft, the solar ultraviolet imager, and the eclipse here. And then we have the space images, and you see at solar minimum, there were very few streamers that went quite far out. This image in the middle now has hotter gas of coronal temperatures. We see a coronal hole here and at both poles here. And we can trace back some of these streamers to the places on the disk, although remember that half of them would be on the far side. Anyway, this was 2019 when the eclipse centered out here in the Pacific, and we got only the end of it here in Chile and Argentina. What are we having now? On December 14th, 2 days from when I'm giving this lecture, the peak is over Argentina, and we're near the peak all across South America. And then a year from now, there's an eclipse that goes over Antarctica and the nearby ocean, where the weather statistics are not very good. So we have a plan to fly, and my colleague Glenn Snyder has worked out the flight plan to go from Punta Arenas out and capture the eclipse out the side window of the plane from the sunrise point, and I'll probably be there. And then in 2022, there is no total eclipse, and in 2023, there's one on the other side that's clips a little bit of Australia. And then 2024, the eclipse goes over, the total eclipse goes from Mexico up through Texas and the American Midwest and northern New England and out in Canada. The people from Predictive Science Incorporated a couple of weeks ago issued a preliminary prediction here for what the corona might be like, and you can see they're holding out for a couple of big streamers on this side, and then more merged on this side, and coronal holes should be visible there. If we go to the logarithmic view to show more of what we can do in a composite, it might look like this. And then just last week, they issued their final prediction. So this was just on the 7th, so it's a week before the eclipse itself. Remember that some of the predictions are on the back side, so they've been around for a couple of weeks and have changed since they went into the model. In any case, here is the final prediction that they made for 2 days from now. And if they treat it to magnify the contrast here or show what the magnetic lines of force are and where the magnetic structures are on the surface of the sun, they have that too. These are the preliminary ones. And this is the final prediction here of all the plumes here and the streamers. So this morning, it was cloudy in Pucón, and the weather forecasts are not good for Monday. So we have a question what to do. Here's my team here at dinner. Theo Boris here is a high school student who's with us. And so there are questions. Do you wait it out and hope the sky clears? Do we go up the Villarrica volcano, where we have an excellent site at some altitude, but it could be in the clouds? There's a lot of traffic, and the coast may not be that much clearer and would be a lot of traffic. So if we go east toward the border, or maybe even over the border, if we can work out the permission to go across the border into Argentina, we will see. So earlier today, I was writing some letters to endorse the group in a caravan of cars with the telescopes, trying to go over the border to go to the east and searching for clear weather on Monday morning. The eclipse itself starts about 4 minutes after 11 o'clock. There are various streaming sites that you can watch on from wherever you are. That's the next eclipse, and then there's an annular eclipse where the moon will be a little further away from average in its elliptical orbit. So an annulus, a ring of the photosphere of the everyday sun, will remain visible. So it won't get dark. We won't see the corona, but there is one in June in about 6 months, and it starts just over the border into Canada. At the moment, Americans aren't allowed to go into Canada. But there'll be even some partial phases visible from New York and the eastern United States. I'm wondering whether we could even get a plane just to go up high and see a little bit of partial phase at the beginning, but the annular part is fun to see, and it will be annular over part of Greenland and over the North Pole. So it would be fun to go on the 21st to the North Pole, and then 6 months later go to near the South Pole. And here's the path I told you about to fly out of Punta Arenas to the sunrise point of this eclipse. And then some people will go at much greater expense onto the ice of the Union Glacier. And there are a number of cruise ships that will be in here. And I wish everybody good fortune with the clouds. In 2023, this is the eclipse that is total in Australia, but you see just this extreme point of Australia, so it would be difficult and expensive to get to. It's annular at the beginning here and at the very end, so it's called the hybrid eclipse, but it really is total through the whole main part. And then it's total in East Timor, and then the color coding is clouds, so it's total over this part of Papua New Guinea, of the country of New Guinea. But this looks like a good chance of clear weather here, so we're pointing towards there for April 20th, 2023. And then there's an annular eclipse that will go over the United States and Central America and South America in October 2023. Everybody around the United States will have a partial eclipse to see there, but it won't go quite as far down into South America for everybody to see here. And then we have a big eclipse back in the United States, that hits land in Mexico, right over Mazatlan, and then Texas, and then with increasing statistics of clouds up through Cleveland and Buffalo and northern Vermont and New Hampshire and out to the Canadian prominences. So here's the weather statistics, which you see is blue is better here than here, and better here than there. So we'll see what happens in 2024. And then later in 2024, there's an annular eclipse, and look where it goes, back in Patagonia again, in Chile and Argentina. So you'll see me again in October 2024. And we saw an annular eclipse from Patagonia. I was in Argentina a few years ago, but it'll be fun to be back in October 2024. And maybe we can all meet in person at that time.
15 seconds. 15 seconds. Oh, it's really moving. 5 seconds.
So as you see, it's exciting to be in the path of an eclipse. And if you would watch for 2 minutes, you'll see it's actually a long time. You have time to take a look, use binoculars, take some photos, take another look. And we had a wonderful time in 2017 in clear weather and in 2019 in clear weather. And I hope things go well on Monday. And then in closing, I'll just say something about a conjunction of Saturn and Jupiter that many of you know about is in the sky. If anybody asks me more about it, I can say more about it. But Jupiter and Saturn are exceptionally close in the sky. So that's another fun thing to see this month. Thank you again, Thomas and colleagues, for inviting me to give a golden webinar. And I would now be glad to answer any questions.
Fantastic. Thank you so much, Jay, for a wonderful talk. All right, so let's go first to the panelists. Are there any questions from the panel first? Felipe, go please.
Yeah, thanks, Jay, for a wonderful talk. I have a couple of questions, one on science. And the variability that you mentioned on the streamers, you can allow to see with the eclipse. Could you, go a bit deeper on that? Could you explain why these oscillations happen and how the eclipse helps in them?
So the question is, why is the corona 1,000,000 degrees hot? And nobody knew that originally. It was finally, there were these strange lines, one in the red, one in the green, especially, that were found in 1869, 1870. And nobody knew what they were. And it turned out that the event Edlen in around 1940, so it took another 70 years, figured out that these were extreme states of iron where many electrons had been lost. So the question is how it gets to those extreme states. And the problem has been solved. But I used to say that there were a dozen different solutions. And then one of my colleagues at the University of Chicago actually made a list a couple of years ago, and there were 17 different solutions. In other words, we don't really know. There were 17 different possibilities. One or more of them may be possible, but the main idea was between what are called Alfvén waves, which are magnetic waves on these loops of gas near the sun, and if they vibrate, they heat the gas around them, and that can spread through the corona. And another possibility is that there are all kinds of little flares going off all the time, so-called nano flares. They would not expect it to have any particular frequency, whereas the loops would be expected to have a frequency of 30 seconds or so, if you calculate the average size of loops, depending on the sizes of the loops. But then Dr. James Hyenson some time ago calculated that there could be a thin sheath on the edge of the loops. And if you calculate the magnetic field in those, we have the surface Alfvén waves, and they would go faster and have sub-second periods. And that would show up in an oscillation of a few percent in the brightness in those spectral lines. So we have very elaborate apparatus with cameras to measure this this brightness very accurately and very rapidly through filters that are specially made with interference properties that allow only the very pure coronal red and coronal green colors to go, and we are, in other words, trying to make a test of the predicted methods, try to discriminate among predictions for methods of heating the corona.
Thanks.
Okay, are there any other questions from the panel? Then let's go to the Q&A. Oh, Hans, yeah, please go ahead.
Yeah. So, Jay, nice to see you again. Do you remember 2001 on the rooftop of the University of Lusaka, where I met you?
Clear sky again in Lusaka
in
2001. I have a big print.
It's about the weather. So you have 34 or 35 eclipses that you have seen. how many of those were close successes or close misses? I mean, how often has the weather cleared in the last minute?
Well,
that is one question.
It's hard to count. I mean, I know I've actually physically been in the path of totality 35 times, and I've always seen something, but sometimes we went up in airplanes, and sometimes in 2012 we had a helicopter standing by, and then sometimes I'm on the ground, and we do choose using predictions from the Canadian meteorologist Jay Anderson of the cloudiness statistics based on 20 years of weather satellite images. So Jay Anderson and I have actually written now the Peterson Field Guide to Weather, which is in press now. We've seen the proof, so it'll be out in the spring sometime. And he and I are both not traveling to this exact one, but we look forward to many eclipses in the future. So, but I am choosing where to go by the cloudiness statistics, and that helps.
Didn't help you in Chile now, but I also wanted to ask or comment that you mentioned looking at eclipses from aeroplanes, and I remember that KAO, the Kuiper Airborne Observatory of NASA, actually was chasing an eclipse once with my friend Eric Beckland on board, and so it's interesting that these high energy phenomena that you see in the corona, 10 million degrees, but there are also experiments where even in the far infrared, which is low energy, you can learn something from solar eclipses. I find this very fascinating.
That's true. And we, when rarely something goes over, Cerro Tololo, we would like to use their big telescopes, which they wouldn't let us do at Cerro Tololo. They don't like us to point 4-meter telescopes at the sun. And there are special water cooling and areas that allow us a small area for this 4-meter new solar telescope, new technology solar telescope known as the Inouye telescope. But basically there's a different network, as you know very well, but I'm saying for the group, of solar telescopes around the world that are just in size and type and different filters than the big nighttime telescopes, which you don't usually want to point at the sun.
Can I ask a final question also related to Chile? I mean, what is the best way to chase or to observe the shadow of the moon coming towards you? I mean, you mentioned you want to go up to the volcano overlooking the Villarrica Lake. Is that a good idea to catch the shadow moving with like 1 kilometer per second across?
If the weather were clear, it would be a good idea. The shadow is coming at 2,000 or 3,000 kilometers an hour, so it's coming very rapidly. But you can see it gathering in the darkness. The higher you are, the better.
10 seconds across the lake.
Well, if it were clear, that would be good. But if it's in the rain, then that's not good. And
but what do you see when you see the shadow? I have never seen a shadow, despite my 5 eclipses that I have successfully observed.
Well, you're usually busy. I'm usually busy doing other things, but it just is sort of gathering darkness, and it just gets wider and wider in the direction that it's coming. And then there's another phenomenon that you again know called shadow bands, which some people study, but those are ripple effects on the ground that come from this narrow crescent of the sun being affected by the Earth's atmosphere. And last time in 2019, they were very obvious. You just look down and there are these ripples coming across the ground. They're only a few percent, so they're hard to photograph, and they're moving pretty quickly. But so there are a lot of wonderful phenomena. Then the temperature drops very considerably. A lot of things going on, and from different points of view.
And if you see something, you will see the galactic center behind your Chilean eclipse now.
Well, I prefer to look up and watch the solar corona and and the chromosphere.
Okay, thank you.
Welcome. Thanks for being here.
Wonderful. Okay, so let's go to the Q&A. The first question at the top is from Ivo Saviane, who is asking, are there any repeats of the Eddington experiment? Is there any statistics over time that sees any, let's say, differential drifts in the effects of general relativity and the displacement of stellar images around the sun?
So to give a 30-second summary, Albert Einstein in 1915 came out with his general theory of relativity, and that verified that the precession of the orbit of Mercury was indeed 43 seconds of arc per century, as had been measured. And Eddington predicted that if you looked at the sun in the sky, they would, and you saw stars near the sun, would they appear to have bent a little bit, passing near the sun? And he wrote George Ellery Hale in 1914, and Hale wrote back, well, you should do this during an eclipse. So there was a young astronomer named Arthur Eddington. He wasn't Sir then, and he was a Quaker who was in danger of being imprisoned for not going into World War I. But they made a deal for him that he would escape prison if he would go on an eclipse expedition for 1919, when there was an eclipse that went across from Brazil to Africa. In fact, Fenley Freundlich in Germany had tried in 1914 to try to measure this effect before Einstein had finished his general theory of relativity, and he entered Russia to go to Crimea on August 1st, 1914, which was the start of World War I. So he was imprisoned, and all the telescopes were seized. They didn't show up for years. So it's a good thing that happened, because he would have found a different effect than Einstein had predicted, and Einstein came up with an additional effect that wound up matching. So in 1919, anyway, Eddington made the prediction, made the observations. He himself was in Principe Island off the coast of what is now Gabon, and another group was in Brazil, and the measurements matched very precisely. And in November 1919, so I just sponsored a meeting, a session at, well, first the European Space Planetary Society, and then the American Planetary Society with some experts on the history of Einstein and relativity. So anyway, this experiment has been tried several times since, and in 1973 there was a big dust storm that made the transparency 10% in Mauritania, so it didn't go so well. So from time to time somebody does it, but it's now become an amateur experiment because the Einstein effect of relativity has been tested more precisely in other ways, especially with radio astronomy and interferometry. There was one scientist, a retired optical physicist, who very carefully worked in 2017 and made some observations, and some other people made some observations that verified it. I have a graph that shows of this agreement here. And I've been invited to participate with them at a secret site in the middle of Mexico in 2024, but I'm not willing to commit myself to anything special now. So it's a qualified amateur event now. It's a nice thing to do with care, but we don't need it to test relativity anymore. We've certainly seen relativity tested, in particular now with this 1.5 million solar mass black hole in the center of our galaxy that Andrea Ghez and Reinhard Genzel won half the Nobel Prize for a couple of months ago.
All right, so let's take the next question in the Q&A from Peter Broughton, who is asking a slightly related question to time evolution, but this time of the sun itself. So does the size or radius of the sun change? And is there any evidence from observations of various solar eclipses towards that trend?
Well, that has been looked at, and that's somewhat controversial. And my personal conclusion in looking at the data is that there is no conclusive evidence that there have been any changes. but there are a few people who think that there have been some slight periodicities. And in fact, there was a big flap a few decades ago when some change was reported that would throw the agreement with relativity out. But then that turned out to be a measurement of the shape of the sun rather than the brightness. Well, it was rather the brightness rather than an oblateness of the sun from an additional effective rotation. So though there are a few people pursuing the size of the sun, I think the data that I've looked at don't show a difference. But now we can measure it more precisely with measuring the Baily's beads, and so over the next decade or so, we'll have a series of observations.
Wonderful. Okay, I see that Daniela has a question.
Yeah, thanks, Jay, for this amazing talk. I have a question for the Q&A from Cecilia Baeza. She said, what's the importance for predicting how the corona will look like? And she said that it's also a great webinar.
Well, we like to understand the effect of the magnetic field and how to put together the equations of some very complicated magnetic field. So the group from Predictive Science has their methods of predicting. There's a big discussion in this a big Nature paper from Nature Astronomy from a couple of years ago, which I was glad to be a co-author for providing some observations. But we want to be able to understand the sun as much as possible and to use the equations to predict everything about it. So we're just trying to help tweak the details of the predictions to make them more accurate.
Thank you.
Let's go to Elizabeth next.
Yes, thanks, Jay, for the very nice talk. I have a question from maybe a combination of two questions from the Q&A from Hernan Gallegos and Debbie McKay. That is, what are the physics behind the cycles of the sun, and why is 11 years? Why is this number particular important?
Well, I think the reason that it's 11 years is not completely known, but there is a differential rotation of the sun that I mentioned briefly, where the equator rotates at a different speed than higher latitudes. And also, as you go in, there's a differential rotation of different speeds as you go in for a while, and that all winds up the magnetic field. We see the sunspots, of course, with this 11-year sunspot cycle. So some people have started really with Olin Wilson decades ago at the Mount Wilson Observatory, measuring the cycles on other stars, because the chromosphere makes a strong emission in the calcium lines that you can follow even in distant stars. And so people have now measured sunspot cycles, or the solar activity cycles anyway, in a variety of other stars. And they're not all 11 years, of course. Some are shorter, some are longer. So the basic physics is understood, but I'm not aware that anybody can actually calculate and come out with 11 years.
Thank you.
Okay, so let's go to Paula. Paula had a question.
Yes, here there are some questions from the Q&A. Thank you, Jay. Very, very nice talk. So here they are questioning, has it been possible to infer from solar eclipses the increasing distances between Earth and Moon?
I think that difference is not measurable from the duration of eclipses, although the method now with the 3D mapping of the moon will eventually show that. But what it can be measured by the laser bouncing of signals off the moon, where these laser corner reflectors that have been put on the moon by the Apollo astronauts. And of course, that's now 50 years old. So they've been bouncing signals off for 50 years. I did visit one laser setup of telescopes at the Mount Stromlo Observatory, where they're basically there in order to measure that distance. So there were the 6 Apollo missions that left these retroreflectors on the moon. I was very excited last week that there was an announcement of 18 potential astronauts on for the Artemis mission, where Artemis was Apollo's wife, and NASA has nominated now 9 men and 9 women to go back to the moon, potentially in 23 and 24, though at the moment NASA's not getting enough money for that, but I hope maybe it will happen while Joe Biden is president in 2024. And one of the astronauts, Stephanie Wilson, as a 13-year-old girl, was given a high school assignment in her town of Pittsfield, about 20 minutes south of where I live. And she was given an assignment to interview somebody. So she came and interviewed me, and she liked what I was doing as an astronomer, and she went on to get a degree in engineering and aerospace engineering, and became one of the astronauts. So she's been up to the space station 3 times. She invited my wife Naomi and me to each of her launches in the family group, and we're so happy now. And even a little surprised, because I thought she might have aged out at age 53 now. But she is the oldest of the 18 people. She's still working in charge of astronaut training assignments at NASA Houston. But as of last week, she's potentially going to the moon, and it's just so very exciting.
Nice, thank you very much, Jay.
Okay, let me ask one more question here from the Q&A. Actually, quite important one. Do the glasses that are being used for the viewing of the eclipse expire and become non-effective at some point?
If you start scratching them or there are holes in them, then you shouldn't use them. But basically, to look up at them for a few minutes every couple of years, there's no reason they shouldn't last indefinitely. One of our Williams College alumni actually made a collection of eclipse glasses, and most unfortunately, he and his wife died in a car accident in Uganda some time ago, and the father, who's a Williams alumnus, gave us the collection, which I have on display at our Hopkins Observatory, the Malin Museum of Astronomy. And there are perfectly good glasses back from 100 years ago, but there is a little ivory thing that I actually don't have on display because I think it's too valuable, with instructions in a little leather case as to how to observe the eclipse in London in 1793. And I haven't tested. I would like to test exactly what the material is and how good it is after those couple of 100 years. I'd like to give it to Ralph Chow, but he's in Canada and I don't want to take it across an international border. So I have to work out a way. Ordinary testing doesn't go through so many orders of magnitude usually. But anyway, just for a few years, for these millions of glasses that are used for eclipses, as long as they're not obviously damaged, they should be fine.
Very nice. One question from Elena Tedler, which is asking, why are the paintings of Russell Butler taken to a secret location? And why are they not shown anymore?
Well, 20 years ago, they took down this beautiful old Art Deco building. And so Butler, in fact, tried to convince the American Museum of Natural History in the 1920s and 30s to put up an astronomical hall, which he never did convince them to do. And eventually they found and they went to the obvious millionaires, Guggenheim's, Rockefellers, who didn't put in money, and they found a more obscure millionaire named Howard Hayden, whose name is now known very well among astronomers because of the Hayden Planetarium in New York and the smaller one in Boston. But they wanted to modernize the whole thing, and they took down the Art Deco building. In fact, there's some damage to one of the paintings because it was hidden behind a panel. It hadn't been on display for the last 10 years, and somebody put an electrical conduit right through it. So anyway, there's just a lot of storage of valuable things from the American Museum of Natural History, and they just don't like the public to know where it is for security reasons. So they asked us not to say where it was.
Okay, so I have a question myself. So there are two different types of corona that are visible, right? There is the red corona and the blue corona. Can you speak a little bit more about that?
Well, I wouldn't say the red corona and the blue corona. We talk of the F corona and the K corona and the E corona. So the E corona are these spectral lines that I told you about. They're so-called forbidden lines because in quantum mechanics, they're very faint. And there's not a good probability of that transition being made. And that's fairly close into the sun where you can see those spectral lines. And that's really from electrons in the magnetic field right near the corona. Now, these loose electrons extend out for a way and have some shape as they're held in those streamers. And so what we're basically seeing is the everyday sun, the so-called photospheric light, reflected towards us from those electrons. And those reflections, first of all, are polarized. So one can make polarization measurements to see what the electron density is in the streamers. And also, the electrons are moving very fast. That's what the million degrees mean. So there are Doppler shifts of the spectral lines. So even though the background photosphere has all these absorption lines that I know you know about, so-called Fraunhofer lines, they're smeared out and we get a smooth set, and maybe only the deepest one, particularization K lines in the region there is a slight dip that's very difficult to measure. So that's called the K corona, from the German word continuerlich, continuous light. Well, you speak German and I don't, but so your accent will be better than mine, but that's the K corona. But then when you go further out, there's some extra light that is scattered towards us from dust particles in the inner solar system, especially near the orbit of Mercury. And that scatters all those Fraunhofer lines, so it's known as the F corona, and doesn't polarize. So if you want to make careful measurements of the corona, we have to do, and this has been known for 50 years, you have to so-called separate the F and K coronas, which you do by looking at the depth of the spectral lines, because only the F corona has those absorption lines, or from the polarization.
Excellent. So let's take the last question from the Q&A, and it comes from Debbie McKay, and Debbie wants to know, how long have you been traveling and recording eclipses?
Well, I'm not completely sure because recently I found in some old photographs from high school a picture of a partial eclipse. So I suspect that I took that picture with my high school made telescope, and I do remember an earlier eclipse that I just saw. But the one that I'm counting as the first took place when I was a first-year student. Freshman, we used to call it, at Harvard, and there was a new program at Harvard to bring the senior professors together with the students, because the Harvard was infamous for the professors not having anything to do with the students; they're just doing their research. So this was the first year of that program in 1959. I was 16 years old, and I registered for a freshman seminar in astronomy. There were a dozen of us, And Professor Donald Menzel was the director of the observatory, a very famous, important astronomer who had studied the sun at eclipses, made some major discoveries and books about the sun, and he took us. And there just happened to be a total solar eclipse, the beginning of which was visible off the coast of Massachusetts. It was decades before I realized that the eclipse was really total, mainly over Europe. But he took us up in a plane, and we could look out and see the eclipse out the window. So that was in October of 1959, and that interested me. And I didn't start going to all the eclipses for a few years, but I've been to basically all of them since 1970, which is coming on 50 years. So I'm particularly upset that COVID has kept me from being in Chile or Argentina this time, but people assure me that this means that I'll still be in good health to see many more eclipses to come. So I wish that for all of us.
Wonderful. Thank you so much to you, Jay, for taking the time to explaining to us your vast experience in observing these eclipses. It's really wonderful to hear your stories.
Thank you very much. It's been my pleasure to know you and to work with you. And I wish you great luck on site on Monday. And I know we will keep in touch.
We will keep in touch. That's right. Yes. Thank you very much to everyone who tuned in. Thank you so much to the panelists for joining us. I also would like to extend a very, very special thank you to my co-host who is leaving us. She took up a faculty position and she will be very busy in the next year. So Evelyn Johnston, thank you so much for starting this series with me. We will try to continue with our new panelists, Maria, Elizabeth, and Demetra, who will be joining the team of the Golden Webinars next year. So please, everyone, tune in again on the 15th of January for our next Golden Webinar, which will be given by Stacy McGaw, who is a professor of astronomy at the Case Western Reserve University in Cleveland, Ohio, who will be giving us some insights on dark matter and the alternatives to that. So please stay safe, everyone. Stay healthy, and join us maybe on the 14th for the live stream of the eclipse. So it seems to lighten up around us up here at the observing platform. So fingers crossed. Stay safe, stay healthy, and until the next Golden Webinar in Astrophysics next year. Bye, everyone.
Thank you very much.